Assalamualaikum to dear lecturer Dr. Rosniza binti Hussein. My name is Ahmad Nazmi from 3BNL. My metric card is DN160176. Okay, today I will introduce about the bullet train. Okay. A train may well be one among form of transport consisting of a series of connected vehicles that typically runs on a rail track to move load or passengers. The word trains originates from the French trahiner, got from the Latin word trahere, which means to pull or to draw. A train includes passenger carrying vehicles that and might usually be terribly long and quick. Bullet train or Shinkansen is a network of high-speed railways lines in Japan. Japan was the primary country to make dedicated railway lines for high-speed travel. To modify high-speed operation, it used a range of advanced technology compared with conventional rail, achieving not only high speed but also a high standard of safety and comfort. Its success has influenced alternative railways within the world, and also the importance and advantages of high-speed rail has consequently been re-evaluated. Bullet trains are electrical multiple units, offering fast acceleration, deceleration, and reduced damage to the track because of the use of lighter vehicles compared to locomotives or power cars. Shinkansen, or this bullet train, use a 25 kilovolt AC overhead power supply to overcome the limitations of the 1500 volt direct current used on the existing electrified narrow gauge system. Material of the bullet train used lightweight aluminium components because it was the key in providing the enhanced speed, safety, and comfort of the new train design. Other than that, some bullet trains are made of aluminium foam or a material that's stronger, lighter, and better in a crash than fiberglass or regular old metal. This research will discuss about the material used for bullet train and will explain how it is built and the processing step involved in the manufacturing process of bullet train. Other than that, the suitable and related diagrams will also be included in this presentation.
Magnesium that used in a bullet train is magnesium alloy. Due to low density and higher specific strength and rigidity than aluminum alloy and steel, magnesium alloy could be used in railway vehicle with less weight. Moreover, magnesium alloy can have better capacity of vibration reduction than aluminum alloys and steel. The application of magnesium alloy could produce weight, vibration, and noise reduction, and improve running safety and higher energy efficiency for high-speed train. The layers are held together by metallic bonding, the electrostatic interaction of negatively charged electron and positively charged ion. While crashes are rare, high-speed trains are regularly hit by small objects which can cause trouble. Aluminium foam has a very hard and comfortable impact resistance, especially for small impact like stone, bottles, or just bird. Say rough of void engineering service.
Hello, my name is Cassandra and I am from 1BNM. Okay, today I will present about the operation from our analysis. Okay, first is planning high speed traffic on new line request. Okay, this is the highly structured train plan metric. And this is the regular interval and asset commercially but also efficient from an operational standpoint, and the maximum use of available capacity, and the operation high quality of service targeted, and the compatibility with maintenance, upgrade, and repair work. Okay, next I will explain about the example of bullet train. The example of bullet train is Tohoku Shinkansen, Maklev Chuo Shinkansen, and Gaussian train. Okay, the first bullet train that I will present is about Tohoku Shinkansen. Tohoku Shinkansen, also as known as E5 series train. The train is capable of up to 320 km/h. It is 200 mph and were introduced on the Tohoku Shinkansen in March 2011. The operation at the maximum speed of 320 km/h between Utsunomiya and Morioka on the road commenced on 16 March 2013 and reduced the journey time to around 3 hours for train from Tokyo to Shin-Amori, a distance of 674 km/h, 419 miles. The extensive trial using the fast technology 360 test train have shown that operation at 360 km/h, 224 mph, is not currently flexible because of problem of noise pollution, particularly Turnabomb, overwear, wire wear, and braking distance. On 30 October 2012, JR East announced that it is pursuing research and development to increase speed to 360 km/h on the Tohoku Shinkansen by 2020. The second example of bullet train is Maglev, the Shuo Shinkansen. Maglev has been undertaking test run on the Yamanashi test track since 1997. Running at speed of over 500 km/h, it is 310 mph. As a result of this intensity testing, Maglev technology is almost ready for public usage. Construction of the Shinagawa to Nagoya section began in 2014, with 86% of the 286 km road to be internal. Maglev derived from magnetic levitation. The meaning of maglev is a system of train transportation that uses two sets of magnets, one set to repel and push the train up off the track, then another set to move the floating train ahead at great speed, taking advantage of the lack of friction. With maglev technology, there are no moving parts. The train is the only moving part. The train travels along a guideway of magnets which control the train's stability of the speed. Maglev trains are therefore quicker and smoother than conventional trains and have the potential for much higher speed. Next is the Gauss-Chen train. This is the track bogies of the Gauss-Chen train GCT. Allow the wheel to be unlocked from the axle, narrow or wideness as necessary, and direct lock. 3 test trains have been constructed, with the second set having complete reliability trials on the Yoshan line east of Matsuyama in Shikoku in September 2013. The third set was undertaking Gauss changing trial at Shin Yatsushiro Station on Kyushu, commencing in 2014 for a proposed 3-year period. However, testing was suspended in December 2014. The principal analytical approach. It is have 2 different approaches to estimate the train resistance have been studied. First, a direct approach using the acceleration to calculate the train resistance as a time series. Next, an indirect approach based on the fitting of a predicted to the measured velocity time series, where the train resistance is implicit in the velocity prediction. And next is 2 variants of the direct approach have been studied. First is the acceleration is calculated or measured and stored as a separate time series. The acceleration is obtained from a stored velocity time series at the given resolution. Due to the infallibility of acceleration measurement, only acceleration obtained from high resolution velocity difference has been evaluated in this work. However, this is believed to give more accurate result than using acceleration measurement because of lower level of noise. Thank you.